Okay, so it's our great pleasure to have Professor Christian Schnell from Stony Brook University, but actually he's now in Bonn. So he's going to talk about finiteness absolute classes in variations of hash structures. So Christian, please.
Okay, yeah, thank you for the invitation. If you don't know what self-dual classes are, don't worry, I'll tell you. Okay, so what I want to talk about is a generalization of this theorem by Catani-Deligne-Kaplan. So that's an older but famous theorem about Hodge classes, and I want to explain to you a generalization of it to this thing called self-dual classes, which is something that was suggested by physics and was really, really, really surprising to me at the beginning when I first started thinking about this. Okay, so let me start by talking a bit about Hodge classes and this theorem by Catani-Deligne-Kaplan, and then I'll get to the actual topic after that. I also want to say that if there's any questions, please, either in the chat or by interrupting, please do ask. I don't know. Okay, so let's start with the result by Catani-Deligne-Kaplan. Okay, so here's just a slide with a little bit of background. So the setting is integral Hodge structures of even weight. So this means that you have an underlying Z module. The complexification has a Hodge structure of weight 2K, this kind of decomposition here. And then we're also going to need a polarization. So that's a certain kind of bilinear pairing on this space with some positivity properties. I'll tell you the exact properties later, but for the time being, it doesn't matter much. Okay, the typical example in geometry would be the cohomology of a projective complex manifold in even degrees. And then the polarization is constructed in some slightly complicated way, but basically by integrating, but then if the degree is wrong, you have to do cup product with the class of an ample bundle in certain ways. So that, you know, the typical thing to keep in mind is when you're doing middle cohomology in degree equal to half the dimension of something even dimensional, for example, on the surface, then the polarization is just basically just integration, except that you have to adjust it slightly to do the primitive, non-primitive parts, okay? And then this, in Hodge theory, something of great interest are Hodge classes. So these are classes that are of type KK, just in the middle piece of this decomposition. And of course, you all know that the reason why people want to know about these things is because the classes of subvarieties are Hodge classes. And then because there's this famous problem, the Hodge conjecture, which says that hopefully, if you have a Hodge class, then at least some multiple of it should come from geometries. Some multiple of it should be a linear combination of such fundamental classes. Okay, so I mean, the Hodge conjecture is really a statement about rational classes, and so this is why there's this multiple, and there's lots of pathologies for integral classes. But for this problem here, we're interested in the integral classes. Okay, and then, well, the Hodge conjecture itself, of course, there's not much is known, but there are some statements that one can make for families. That's where this Catani-Deligne-Kaplan theorem comes in. Okay, so I changed the notation, and I have X just a smooth algebraic variety, which is some kind of base or some kind of parameter space. And then I have a variation of Hodge structure over it. So that's, roughly speaking, a family of Hodge structures that are parameterized by the points of X. So more specifically, you have a local system, a locally constant sheaf, whose stalks give you the different vector spaces. And then at every point, you want a Hodge structure on that thing. And then you want it to vary in some specific way, but that doesn't matter for us. Okay, so this is the kind of thing that you get when you start from a family of smooth projective varieties, and then you look at the cohomology of the fibers. The local system would be the higher direct image of the constant sheaf. Okay, and so in this case, the Hodge conjecture makes some predictions about sets in X. Namely, this is an observation by Weyl. So he said in his book that if you look at the set of points in the base X, so you go to one of the points, you fix one particular integral class in the cohomology of the fiber. And then you do parallel translation, you move it to nearby fibers, and then you look at the locus of points in X where some translate of this class is a Hodge class. Right? If the Hodge conjecture was true, then this sort of set would be the set of points where some cohomology class is the cohomology class of algebraic cycles. And anyway, one can then deduce by some standard argument that the set of points would have to be an algebraic subvariety if the Hodge conjecture was true. Okay, and even though the Hodge conjecture isn't known, amazingly, Catani and Kaplan were able to prove this. So this is a very famous paper in Hodge theory in 1995. They showed exactly this. And in fact, they get a bit stronger conclusions because their theorem is actually for arbitrary variations of Hodge structure, even when they don't necessarily come from the cohomology of a family. Okay. Again, I'll state the precise result in a second, but let me say that the point of this theorem is that for many practical questions, this is almost as good as the Hodge conjecture in the sense that if you have an individual variety, you cannot say anything of Hodge conjecture type. But when you look at families, you get the sort of consequences that you would get out of the Hodge conjecture, right? For example, if you go to some moduli space, inside some moduli space, you look at the set of points where some kind of Hodge theoretic condition holds, well, that will be an algebraic subvariety of your moduli space by this theorem. And there's also some kind of arithmetic implications that have been studied by Voisin about this question, to what extent Hodge classes are absolute Hodge classes. But anyway. Okay, now to connect it with what I want to talk about, let me give the more precise result, because in fact they prove something stronger. So what they actually do is they take the vector bundle on X, whose fibers are the vector spaces on which these Hodge structures live. This vector bundle is originally just a complex vector bundle, but in this situation, one can show that it actually has a uniquely determined algebraic structure. Okay, and then inside of this bundle, they look at all the points that correspond to integral Hodge classes. Okay, so a point in the bundle is a point in X and then a vector in the fiber. And then you look at those places where the vector in the fiber is a Hodge class in that Hodge structure. And you also put some numerical bounds. So you bound what you can think of as the self-intersection of the class. So there's this polarization form Q, and you just look at only classes where this has a fixed value. And then what they actually show is that this set is an algebraic subvariety of this bundle. So this is not just controlling the set of points in the base, but it's also controlling how the class sort of varies with the point, right? They show that this is an algebraic subvariety of the bundle, and also it's proper and finite over the base X. So at points where you have Hodge classes, you can only have finitely many, once you have this numerical condition here. Okay, this is the actual theorem. Okay, and so this is actually, from a point of view of geometry, a very surprising result, actually. So I'm quoting Claire here from a survey paper that she wrote about Hodge loci. And so she says that this theorem is in fact stronger than what is predicted by the Hodge conjecture. And especially the finiteness part is quite intriguing because it is not predicted by geometry. So the point is that integral Hodge classes have all sorts of pathologies, which is why the Hodge conjecture is just over Q, but still this is a theorem about integral classes. Okay. So just again, as a motivation, let me explain a little bit where this finiteness comes from. The algebraicity part is very difficult, so I won't say anything about that, but at least let's understand why, once you fix this value of the pairing Q, why there's only finitely many classes at every given point. Okay, so the pointwise finiteness. So for that, I have to remind you how the polarization works. So for the polarization, you define this auxiliary operator called the Weyl operator. This acts as I to the P minus Q on the PQ subspace. And well, if I have an integral, if I have a Hodge class of type KK, then I get an eigenvector of this operator. Okay, and then the condition to be a polarization is that when you take this pairing Q and you stick in the operator C, it means that you make these sign changes by these powers of I on different parts of the decomposition, then you get something positive definite. That's the positivity condition. And also the decomposition needs to be orthogonal. Okay, so then you get a norm on the vector space, which is called the Hodge norm, by just taking this positive definite inner product. And now if I have a Hodge class, then what happens is that the norm of that class, which is by definition the pairing of the Weyl operator applied to V and V, well, that's actually just the self-intersection number of the class, because the thing is an eigenvector. And so if I'm bounding in this theorem, if I'm bounding the self-intersection number, then I'm automatically bounding the Hodge norm. And so at every point, what you have is, well, you have this ball of a fixed size in the fiber, which is the Hodge norm less or equal to Hodge norm equal to Q. So it's not a ball, it's a sphere. So you have the sphere of a fixed size, and then you're intersecting it with a discrete subset of the integral classes. And so that's finite. It's this compact intersected discrete. So this is kind of the easy part of it, the finiteness of every fiber. And then the difficult part of the theorem is to show that the finiteness is sort of uniform, that even if you move towards the places where the Hodge structures degenerate, you still keep some kind of uniform finiteness. Okay, are there any questions at this point? You good? Okay. Okay, so now the actual story for this talk starts in late 2019. So at that point, I got an email message from Thomas Grimm, who's a theoretical physicist at the University of Utrecht. And he said, well, for some physics application, I started looking at this Catani-Kaplan paper. And it seems to me that even though they look at Hodge classes, there should be a more general statement where we don't assume that classes are Hodge classes, but that they're just so-called self-dual classes for the Weyl operator. I'll give the definition in a second. And then he said, well, I realized that probably in that case, this kind of algebraicity statement is totally false, but I'm hoping that there could be some generalization of the finiteness part at least, because that would be very useful for my string theory applications that I want to do. Are you aware if any such thing has been considered in the literature? Okay, so my first reaction was no, no such thing has been considered. Also, I don't think this can be true because I actually went through the proof of Catani-Kaplan quite carefully at some point. And there's a lot of places where it crucially uses this condition that you're doing Hodge classes. It's some kind of complicated induction where at every step you need some vanishing that comes out of this Hodge class condition. And so I didn't think that this could be true. But then I started computing a bunch of examples. And somehow in each example that I computed, I thought I can easily make a counterexample to his question. It turned out that what he wanted is actually true. And so then I started thinking about this. Okay, so maybe I should tell you what self-dual classes are. So again, the Weyl, it's defined in terms of the Weyl operator, right? So this is this operator. Since we're doing Hodge structures of even weight, the way this actually works is that the Weyl operator is something who squares the identity. So all the eigenvalues are actually plus minus one, right? In this formula here, what the Weyl operator does is really just change the sign. On the space in the middle where the Hodge classes are, it's the eigenvalue is plus one, and then the eigenvalues alternate. The next one it's minus one, and the next one is plus one again, and so on. Okay, and so this notion of self-duality that he was interested in, this is a generalization of Hodge classes where you just look at classes that are integral and that are eigenvectors for the Weyl operator. So you're not just assuming that it's of type kk, but you allow all the types that differ from the type kk by steps of 2, all the places where the eigenvalues are plus 1. And then of course you would have this notion of being anti-self-dual, which is the -1 eigenvectors, right? So Hodge classes are always self-dual because they are always by definition in this place where it's plus 1. But you get many other interesting examples. So specifically for physics, say if you have a fourfold, so the physicists would want like a Calabi-Yau fourfold, then classes of type 4,0 plus 0,4 would be self-dual. Right? Because again, on those places, the eigenvalue is plus 1. On surfaces, if you look at integral classes that are of type 2,0 plus 0,2, those would be anti-self-dual, for instance. On those spaces, the Weyl operator is negative. Okay. Now, what is the meaning of this condition, and why do they care about it in physics? So the meaning of the self-duality condition is that you're actually looking at classes that have a sort of minimal norm, minimal possible norm. And so here's the precise argument, right? If I take any integral class, I can use the decomposition into eigenspaces of C and decompose it into a positive and a negative part. The positive part is where the Weyl operator has eigenvalue 1. The negative part is where it has -1. And then if I compute the norm, the Hodge norm of this V, because the different spaces are orthogonal, it breaks up like this. I can estimate it from below by subtracting the negative part. And then the thing on the right-hand side is exactly the self-intersection number. Okay, so you see that the negative part is 0 if and only if the norm of V is as small as it can be, which is the self-intersection number. So so a class is self-dual if and only if its Hodge norm achieves the smallest possible value, namely the self-intersection number. So this is the interest of it. This is sort of how you should think of this condition, right? Otherwise, from the point of view of Hodge theory, it looks very unmotivated because there's no geometric meaning to these classes that are not Hodge classes. But from this point of view, they're still interesting. Okay. So here's a little, my attempt at sort of explaining how this comes up in physics. I'm not a theoretical physicist. I have no understanding of exactly what they're doing, but so this is just a sort of cartoon version of the story, okay? So the kind of thing Grimm and his friends want to consider is X would be, for example, a Calabi-Yau fourfold. So the 4, 0, and 0, 4 spaces have dimension 1. And then their terminology for integral classes is integral fluxes. So a class in H4 with integer coefficient is an integral flux. And then they have self-dual and anti-self-dual fluxes. The self-dual ones are the type of 4, 0, 2, 2, and 0, 4. The anti-self-dual ones are 3, 1, and 1, 3 in the Hodge decomposition. Okay, and then what they actually need to construct some kind of physical theory is a pair of a Calabi-Yau fourfold and one of these integral fluxes. And then they will let the Calabi-Yau fourfold vary in the moduli space, and they put the self-duality condition that the flux is of type 4, 0, and 0, 4. And then this condition that occurred in Catani-Deligne-Kaplan, that the pairing, the self-intersection number is fixed, this is for them is some kind of consistency condition where the pairing in this case is just the integral of V cup V, and this expression can be computed in some different way and turns out, and so the value turns out to be determined by some other parameters in the theory. Okay, so then they're looking at pairs XV where the self-intersection number is fixed and X can change in moduli. And then the Hodge norm of the class is some kind of energy somehow. And so when you look at self-dual fluxes, what you're looking at is places, so pairs XV, where this energy is somehow minimized. That's how it comes up in their setting, okay? And so as usual, you expect that the set of places where you minimize some energy should have some special structure and should be nice and well-behaved and so on. And so consequently, several different physicists, started by Douglas and then Ashok Douglas and then also Grimm and some of his collaborators, they started predicting that the number of these self-dual fluxes should be finite. So when you look at the pairs XV, where you put this consistency condition and then you let X vary in moduli and that you let V vary arbitrarily just subject to this condition, you should get only finitely many things somehow. Okay. So this is kind of the interest, right? So this is totally orthogonal to algebraic geometry. In algebraic geometry, I don't think there's any meaningful interpretation of the self-duality condition at all. It's only the Hodge classes that are somehow tied to geometry. But from their point of view, this is a very natural generalization. Any questions? I see someone picking up the microphone.
So for
yes?
anti-self-dual,
Yes.
the energy turned out to be negative. Why?
No, the
My
energy is
physical
not.
understand everything should be positive. Why we have a negative?
Yeah, no, the energy is not negative because the energy is always the Hodge norm, so it would still be positive, right? If for anti-self-dual cases V is equal to V minus, then you're just dropping the V plus part. But then you don't. Then the self-intersection number would become negative.
All right,
so the anti-self-dual ones are where the energy is equal to minus this number Q.
Okay, thank you. So to my understanding, in physics, if you have something have energy, to me, it should be related to some kind of fear, physical fear. So now we have a subvariety. Do we have any nature physical fear associated to the subvariety?
That I cannot answer that. Sorry. I mean, as I said, I'm not a physicist. I mean, maybe they have some interpretation geometrically for what it means, but it doesn't. I mean, it cannot be like an algebraic geometry type of thing. I think. You could imagine realizing the cohomology class by some kind of non-algebraic sub-manifolds or something like that, subvarieties, but it is definitely not algebraic geometry once you leave Hodge classes. Okay. Are there other questions? Good. Okay. All right. So let me also give two small examples here so that you can see kind of what happens with these classes. So for Hodge classes, Katanidin-Kaplan says that the sets that you get are algebraic. For these self-dual classes, the sets are not algebraic. Okay? So one simple kind of example is when you do K3 surfaces, unpolarized. So the moduli space is a quotient of some period domain, has complex dimension 20. And the period domain has this very concrete description, right? Like the whole Hodge structure is just determined by the 2-0 part, which is rank 1. And it's a set of points in some 20-dimensional quadric where a certain pairing is negative definite. And so now if I fix an integral class in the integral lattice of the K3, and then I look at the set of points in the moduli space where that fixed integral class is self-dual of type 2-0 and 0-2. Well, then you can actually write down in terms of the 2-0 space what the condition is, right? Because this means that the Hodge components of V can only occur in type 2-0 and 0-2. So they have to be proportional to sigma and sigma conjugate. And if you write it out, you end up with this equation here.
Excuse me?
Yes.
You said on surface 2-0 plus 0-2 is anti-self-dual, right?
Yeah, yes, you're right. This is a typo, indeed.
Oh,
yes, it's anti-self-dual, sorry, not self-dual.
Okay.
Yes. The set of points where it's anti-self-dual is given by this equation here. And you see it involves not just sigma, but also the conjugate. And so if you think about it, there's actually 20 real conditions here. And so this turns out to be a totally real submanifold of real dimension 20. Totally real means that the tangent space doesn't contain any complex lines at any point. Okay, so this is quite orthogonal to an algebraic subvariety. In other simple examples, this is the kind of thing I would look at as a Hodge theorist. Like there's some toy models for variations of Hodge structure on a puncture disk, so-called nilpotent orbits. In those cases, you can compute everything explicitly, and you find things like this: that the set of places in the parameter space in the puncture disk where some given class is self-dual, it can be some line segment that goes into the origin like this. Again, yes.
Oh, how do you get this real submanifold of real dimension 20? How did you get it?
So the condition is that the class V has to be of type 2-0 and 0-2. So the 2-0 part has to be a multiple of sigma, and the 0-2 part has to be a multiple of sigma bar. And then I just take the pairing with sigma and sigma bar, and when I solve for the two components, I get these numbers.
Oh, why are these two same? Q sigma bar V is equal to this one?
Well, because so you write V as whatever A times sigma plus B times sigma bar, and then you evaluate the pairing against sigma and sigma bar. And when you solve for then you get two equations for the two coefficients, and you can solve.
Oh, thank you.
Okay. So anyway, so this is sort of these are typical examples. All right, so then maybe I will tell you now what the main theorem is. So it turned out that fortunately there is a generalization of Katanidin-Kaplan that can be proved, although the methods are quite different. So I'll explain that also. So I will now go back to the setting of Katanidin-Kaplan. So X is a smooth algebraic variety, and I fix an integral variation of Hodge structure with even weight. Again, if you want, you can think that this comes from a family of algebraic varieties. And again, I take the vector bundle E, which is the vector bundle whose fibers are these Hodge structures, and this bundle has an algebraic structure. And then here's the result, okay? So we do the same thing as in Khatani-Dehn-Kaplan. We look at the set of points in the bundle where the class is an integral self-dual class, okay? Again, points in the bundle, I think of as points in the base and the vector in the fiber. And I ask that the vector in the fiber should be integral, should be an eigenvector of the Weyl operator, and it should have a fixed self-intersection number. I call this the locus of self-dual classes. Okay, now this locus is not algebraic, right? Because you see these examples over here. So the replacement for it is that it is still nice in the sense that it is definable in a certain O-minimal structure called Rnx. So this, I will explain this on the next slide, what it means. So it is not algebraic, but it is still well-behaved or tame or something like that. It's kind of close to being algebraic in that it's describable in using certain functions that are not so far away from being algebraic functions. And the second part, the properness with finite fibers, that stays. That's the same, by the same argument, in fact. And so the good thing about these O-minimal structures and things definable in them is that you have strong uniformity statements. So if at every point, if something is definable, and at every point the fiber is finite, then the number of points in the fibers is actually uniformly bounded. And so we get in particular the conclusion that the physicists wanted, that when you look at these self-dual classes, the number of classes that can occur is, the number of that is uniformly bounded. This started as just a joint project with Grimm, but then there were some reasons why. So anyway, it's a joint project now with Ben Baker and Jacob Zimmerman, who are some of the people who have worked on these O-minimal structures recently in the applications, and then Thomas Grimm, who's a physicist. Right, so yeah, anyway, so this is the fact that O-minimal structures are useful for studying Hodge theoretic problems. This is a quite recent discovery, but so this partly goes back to work by Klingler, partly by Baker and Zimmerman, and there's a very big recent paper by Baker, Klingler, and Zimmerman where they study period mappings using O-minimal structures. And so this is sort of some of the input. Okay, so yeah, please.
So
yeah, of course.
The theorem is a generalization from Hodge class to self-dual classes.
Yes.
The conclusion is the same.
The conclusion is the same, except that we lose algebraicity, right? Because instead of being algebraic, we can only say that the set is definable in this, this logic sort of language. Okay, so I cannot give you a very long treatment of O-minimal structures. Anyway, so if you want to read about this, there's lots of good articles about this now because these guys have worked on sort of Hodge theory and O-minimal structures. So for example, there's a very nice Bourbaki talk by Frezan that discusses O-minimal structures and their connection with Hodge theory. So that would be recommended reading, for example. Also, Baker has given a set of lectures at the Hausdorff Institute 2 or 3 years ago. And again, there's some lecture notes online that are very good. So just very quickly, O-minimal structures are sort of a generalization of algebraic geometry when you think about classes of sets that are bigger than just algebraic sets, okay? So a good description is in terms of structure. So what you do is for every dimension n, you look at, so a structure is that for every dimension n, you specify a certain collection of sets, Sn. And these are subsets of Rn, and these are the sets that are considered nice somehow. And the conditions are these that, so you want your nice sets, sorry, actually, so the sets are called definable, right? So you want the definable sets to be closed under finite unions, intersections, complements, and so on. You want all the algebraic sets to be definable. You want the product of two definable sets to be definable. And then you want any projection of a definable set under linear projection to be again definable. Okay, so these are the conditions. So this kind of becomes our universe, right? So if we have a structure that's bigger than just the algebraic sets, then we're allowing more sets into our kind of geometry. And then a function can be definable if its graph is definable. So we just look at the graph, which is a subset of Rm plus n, and then you ask if that's definable. And so the typical examples that are relevant for geometry are these four. So first, you can look at all semi-algebraic sets. Just the algebraic sets themselves are not a structure because they're not closed and are complements, right? So you also need to allow complements of algebraic sets, and then you can actually, since it's real, you can get some inequalities also by taking sum of squares and so on. So you get all these semi-algebraic sets, and that's definable by a theorem by Tarski. You can enlarge this to also allow analytic functions, so convergent power series. Analytic functions are not well behaved, and so you have to tame them by doing restricted analytic functions. So this means that you look at, for example, at functions on the unit cube that are actually real analytic on a slightly bigger open set. So you eliminate bad behavior near the boundary by just doing over-convergent things that are real analytic on a slightly bigger set. Okay, in the structure, maybe you just include these functions, and of course you have dilations and so on. You can get any function that's defined on the neighborhood of some compact set. And this is also an example of a structure. For geometric applications, it's important to have the exponential function usually. And so there's also a structure called Rx, where you allow the exponential function, the real exponential function. And then finally, the structure Rnx in our theorem. This is the most useful one. This is kind of some kind of amalgam of the two. It contains both the restricted analytic functions and the real exponential function. And this turns out, yes, please.
So number 3 is contained in number 2, no?
No, because this is, you're not restricting it, right? Here it's the entire graph as a subset of R2. It's important to have the whole thing, including at infinity. Yeah. Indeed. Right? And once you have this, you can flip, and you also get the graph of the logarithm, for example. Okay, no, it turns out that a lot of stuff in geometry cannot be described by algebraic geometry, but it can be described if you have restricted analytic functions and the exponential function. So this is quite a useful enlargement of algebraic geometry. Okay, and then the crucial definition that comes from model theory is which of these structures are nice. So the nice structures are the so-called O-minimal ones, and these are the ones where the definable sets in dimension 1 are just finite unions of points and intervals. Okay? So in other words, you ask that in dimension 1, the only sets that you can define, the only sets that you consider are still semi-algebraic sets, namely points and intervals. This looks like a really weak condition, but it's a very strong condition because you have this fourth axiom about projections, right? So this says that if I take any definable set in high dimensions and I project it down into dimension 1, I need to get something that's a finite union of points and intervals. And so this has some very strong finiteness implications, actually. All 4 examples over here are known to be O-minimal. This is a big collection of work in model theory, mathematical logic, by these people here, Tarski for R-alg, and then the final result for Rnx by Van den Dries and Miller. So these are fairly difficult theorems, I'm told. I mean, I haven't looked at them. But it means that the structure Rnx is nice for doing geometry. And in that side of the world, people have also developed a whole sort of geometric language for dealing with these things. So you can talk about, for example, definable topological spaces. So these are topological spaces with a finite atlas where the transition functions are definable, right? You can do definable manifolds, definable complex spaces, what have you. And it turns out that as long as the structure is O-minimal, the resulting geometric theory is very close to algebraic geometry. You have a good dimension theory for these objects. You have finite cell decompositions with nice cells. You get some very strong uniform finiteness statements that you're used to from algebraic geometry, and so on and so Okay, so this is sort of the setting that we use. Okay, so let me state the theorem again. I just copied it from the previous slide. So what does definable mean when I said it's definable in this O-minimal structure? So what this actually means is that this space E, this vector bundle, is actually an algebraic vector bundle. An algebraic variety is in particular a definable manifold in the structure R-alg, right? Because I can cover it by finitely many affines, and the transition functions are given by polynomials. So. And then, so to say that this subset of this algebraic bundle is definable, what this means is that if you enlarge your structure from R-alg to Rnx, then you have enough functions to describe this subset here. Okay, so this is some sort of statement that, roughly speaking, you can describe these sort of sets by some big conglomerate of algebraic functions, restricted analytic functions, the real exponential function, stuff like that. That's what it means. Okay, and I already said this uniform boundedness, this is a consequence of the finiteness statements of minimal things. Okay, so that's the statement. So I want to spend the rest of the time really giving a sketch of the proof. So let me ask again if there are questions or if the statement is clear.
Excuse me?
Yes.
Could you give us an intuitive why you have a definition of zero minima? What's the what's your mind?
You mean why this energy condition turns out to be definable or something?
That's right. That's right.
This is a brilliant question. Yeah. No, I don't know. It would be really nice if there was like a direct sort of even heuristic argument. No, I don't know. Maybe this is something that if this O-minimal stuff catches on in physics, maybe the physicists will come up with a heuristic reason why this should hold. But yeah, I think this is sort of the key question. Is there some kind of general principle that would say that like minimizing energy somehow leads to? Yeah. Other questions? Well, okay. So there's three inputs into this theorem. The first is that variations of Hodge structure, which can also be described by so-called period mappings, as you may know, these period mappings are definable in the structure Rnx. This is a very big theorem by Baker, Klinger, Zimmerman from 2 years ago. And then there's some other input, so-called Siegel sets and some morphisms of arithmetic quotients of algebraic groups, and then some lattice theory. I hope to give a little bit of a sketch of how the proof goes. So I should say that this is going to be a little difficult, maybe. So I don't know if it's such a suitable thing for a talk, but then at least you will kind of see maybe where this comes from. I will also say that the Catani-Deligne-Kaplan proof is very much more difficult. So I can spend 20 minutes and give a reasonable sketch of how this is proved. For Catani-Deligne-Kaplan, you couldn't even get started setting up the notation in 20 minutes. You need a whole lecture series to even say what's going on. Okay, so this proof is, this is in particular, this gives you back a new proof of Catani-Deligne-Kaplan that is really much simpler than the original one. Okay, so the outline of the proof, first there's a little bit of heuristic. So like in the case of K3s, for example, Hodge structures have a moduli space. This is the so-called period domain. But for our theorem, we don't actually care about the Hodge structure. We only care about the Weyl operator. And the Weyl operators also have a sort of moduli space. This is what's called the associated symmetric space of the period domain. So there's a real group and the quotient by some maximal compact subgroup. Okay, so I'm going to set up a little bit of notation here, but just on this slide. So I fix a point. And at that point, that reference point in X gives me a particular choice of free Z module, complex vector space, pairing, Weyl operator, and inner product. So this is all the data at one particular point. This is I use as a reference point. And then this data determines a group, a real group, namely just the orthogonal group of the pairing. This is some kind of symmetric pairing that is positive or negative definite in different spaces. So this is some kind of orthogonal group with mixed signature. This is actually an algebraic group, which is reductive. And the real points are the things that preserve this pairing. And then because I have an inner product, I get a maximal compact subgroup, namely the stabilizer of the inner product. Okay, so again, these are elements of this group that the condition turns out to be that you have to commute with a Weyl operator. So this is exactly the stabilizer of the inner product. And then the symmetric space, G mod this maximal compact, its points really correspond to Weyl operators, in the sense that the coset of K by some element G corresponds to the conjugate of our reference Weyl operator. Okay, so this is sort of in some problem where I'm looking at just Weyl operators in some VHS, this is the natural target to look at. And then we're also going to use the arithmetic group coming from the lattice. So the elements of the group that fix the lattice, that have integer coefficients and preserve the lattice. Okay, so then the first point is this theorem by Baker, Klingler, Zimmermann. So we have our VHS, our hot structures. At every point in X, I have a Weyl operator on the fiber. And it turns out that you can make a well-defined mapping to this moduli space. So if you quotient out by this arithmetic group. Okay, so what we're doing is to every point in X, we associate the Weyl operator, but we have to identify the lattices at other points with our reference lattice. And so that involves some conjugation by these by elements in this arithmetic group. And so we also, to get a well-defined map, we have to mod out by this group gamma. In fact, it would be enough to mod out by the monodromy group of the variation of hot structure, or the monodromy group of the local system. But here we're going to this bigger group. We just take the whole arithmetic group. Okay, so again, if you've seen any sort of applications of period domains and period mappings, usually people would mod out by gamma, which is the monodromy group. In this case, we don't do that. We have to do the whole arithmetic group, and this is very important. And anyway, so we have this mapping, and what Baker, Klingler, Zimmermann showed is that this quotient of the symmetric space by the arithmetic group has a structure of a definable manifold in the structure RL. And also this period mapping up here is actually definable in this larger structure R and X. Okay, so this is a very sort of clean statement of the properties of variations of hot structure that people studied in the 80s, that Katani, Kaplan, Schmidt, and so on, Kashiwara, Kawai studied. The way this is proved is by some careful local analysis of what variations of hot structure can look like on the complement of a normal crossing divisor, and really some explicit sort of description in terms of restricted analytic functions and the exponential function. But these two lines are like, they're compressing all that stuff into some very clean result that's very useful. So once you have this result, you don't really have to look again at the sort of local Hodge theory and degenerations and so on.
Excuse me.
Yeah, please.
The period mapping is passing through the original.
It passes through D mod gamma, yeah, exactly.
Okay. Thank you.
Yeah, and so what they actually prove is the definability of this period mapping with the Weyl operators. But then there's a formal argument that implies that when you map to D mod gamma, it's also definable. But the real content is the definability of this mapping.
So what's the dimension, difference of dimension of the period domain and this one?
Well, so in the period domain is a quotient GR by some group which is not maximally compact. So this is smaller.
Smaller.
Yeah, you in the period domain you mod out by some subgroup of this K.
I see. Thank you.
Yes. For our theorem, we're actually not looking at loci in X, but loci in the bundle. But it turns out that you can lift this to a mapping on bundles. So on this arithmetic quotient, so this arithmetic quotient I think of as like the moduli space of Weyl operators. Over that, I have a universal bundle with fiber this reference vector space. And I mean, again, you just define it by a quotient, right? So the group gamma doesn't just act on the cosets G mod K, but of course gamma also acts in the vector space. And if you take this quotient, then you get something which is naturally a bundle with fiber HC over here. This is sort of the universal Hodge bundle, if you want. This lives over here. this mapping on Weyl operators can actually be lifted naturally. And one can show, based on this theorem, that the lifted thing is still definable. Okay, so our algebraic vector bundle maps into this our alg definable vector bundle, and the mapping between them is still definable in this big structure Rnx. Okay, and so this actually reduces our problem very drastically. This turns our problem about self-dual classes in a variation of Hodge structure into a sort of universal problem of studying self-dual classes in this universal bundle, right? Because suppose I manage to show that the locus of self-dual classes in this universal bundle here is definable, right? So this is describable by things in our algebra. Well, then it's a definable set. Then the locus of self-dual classes that I'm interested in is the pre-image of this definable thing by this definable mapping. And so it will be definable in E. Right? So all I have to do is I have to take the universal locus of self-dual classes and show that that's definable in the structure alg. And then the theorem here takes care of the definability of the original thing. Okay, so this is nice because then you don't have to deal with the specific variation of Hodge structure and its asymptotics near the boundary and stuff like that. You're just now dealing with a problem about algebraic groups. You just have this algebraic group, you have a certain sublocus of there, and you want to describe it by some equations. Okay, so this is sort of the nice feature of this. If you use this theorem sort of as a black box, you can turn some questions about variations of Hodge structure, like our specific one, into just questions about these arithmetic quotients. Okay, so let's do that, right? So what we now do is we look at the set of points in this universal bundle that are self-dual classes. So specifically, the points in here are these pairs, a coset, which corresponds to a Weyl operator, and then an integral in the class. And then I want those things to be self-dual. So I want the class to be integral. I want the class to be self-dual for the corresponding Weyl operator, which is this conjugate. And then I want to have a fixed value of the self-intersection. This is the locus. Okay, now the question that comes up at this point is, well, how could this kind of locus possibly be definable in an ominimal structure? Okay? Because we're including here an infinite discrete set, namely this integral lattice HC. And we're allowing infinitely many elements of there because this V can vary over all of HC just subject to this condition. Right? But I told you that stuff that is definable has to be somehow finite. Like you're not allowed to define any sort of infinite discrete set because then you violate this ominimality condition. So how can this possibly be true? And well, there's a nice miracle that happens. And the miracle is a result from lattice theory. So the result from lattice theory is a theorem by, I guess it goes back to Minkowski and so on, but the specific one is in a book by Kneser. So it says that this condition here, that you fix the self-intersection number of V, this actually forces some kind of finiteness. This has infinitely many solutions, the number of V's, but the number of solutions fall into just finitely many orbits for the arithmetic group gamma, right? So in this case, this arithmetic group gamma is actually the orthogonal group of the lattice, HZ, with this symmetric pairing. And if I look at the set of integral points for which the value of the pairing is fixed, the group gamma acts on that with just finitely many orbits. Okay, and so because in this bundle we're quotienting out by gamma, we can hope to get some finiteness. This theorem here really requires the group gamma to be the full arithmetic group gamma, the full orthogonal group of the lattice. So if we took the smaller monodromy group of the DHS, we wouldn't have this finiteness, it wouldn't work. Okay, so this is quite important. Okay, so once we have this finiteness, we get a further reduction because now because there's only finitely many orbits, we only have to study a single orbit. If a single orbit is definable, then the finite union is definable. So this means we can now fix an integral class fixed varying value of this pairing. And then we just look at the part of this locus where the integral classes are just in a fixed orbit. I can also assume that my fixed class here is actually self-dual, right? Because if there's no self-dual integral class, then that orbit doesn't contain any self-dual classes, then the locus is empty, so I don't need to consider it. So I can assume that I pick a representative that is actually self-dual. Right, so now inside of this universal bundle, I now get just these two conditions. V is in a fixed gamma orbit, and the class should be self-dual. And now I want to explain why this is definable. And this will also hopefully give a bit of insight into how this definability works. Okay. So one other small piece of notation. So the big symmetric space G mod K, the points of there correspond to Weyl operators. And our choice of A gives us a smaller group and a sort of upgrade of this dictionary here. So once I have A, I can look at the subgroup of those things that fix A. This is still a reductive subgroup, still has a maximal compact by you just intersect everything with the subgroup. And then I still get a symmetric space, a smaller symmetric space, which is GA mod KA. This naturally embeds into this bigger symmetric space here. And so under this dictionary, the points of the smaller symmetric space correspond to Weyl operators that fix this class A. This is a little calculation, but it's not very surprising, right? Okay, and so now I'm going to give you the sort of key calculation that explains how this works. Okay, so let me take, as in over here, let me take our class in this locus. So I assume that I have a point which is self-dual and is in this particular locus, so that the integral vector V is in the orbit of A. And it's in the kernel of the Weyl operator, right? So since V is in the gamma orbit of A, I can write V as gamma of A for some little gamma. And then I can rewrite this condition to be self-dual in this way. And so this says that this Weyl operator, which is this particular conjugate of C, this stabilizes A. And so therefore it is actually, by this dictionary, it's of the form HC H inverse for some element A, H in the stabilizer of A. So I can write it like this. And then if I rewrite this identity, I get that H times gamma inverse times G conjugated C, H gamma inverse G stabilizes C under conjugation, so therefore it belongs to this maximal compact K, which means that these two cosets are the same. And anyway, so then it says that my original point, which was the gamma orbit of this GK and V, is actually of the same as the gamma orbit of a point of a specific type, where the vector V is just A, and where I'm only doing cosets of K for the smaller group, GA. Okay, so this is sort of the calculation that you have to do. So it says that the points in this locus, in the fixed gamma orbit, they actually come from this smaller symmetric space with a subgroup GA. Okay. So this is sort of the description, right? So it takes this locus that we're interested in, which was given by these two conditions, and it says that this locus is actually itself a symmetric space, or a quotient of a symmetric space, where the symmetric space now comes from the smaller group GA. Okay, so anyway, if I summarize the conclusion is that the locus of self-dual classes in a single orbit of the arithmetic group gamma is actually the image of this mapping here, where I have my universal bundle here on the right, and I have this smaller arithmetic quotient of the smaller symmetric space on the left, and I just get this image. This is what this calculation shows. It's not hard to show that this is actually an embedding, so this really says that this locus is actually itself an arithmetic quotient. Okay. And so now we can get definability from another theorem in this paper by Baker, Klingler, Zimmerman, which is actually one of the things that is needed to put like definable structures on these quotients. It just says that in this kind of situation where I have a big reductive group and an arithmetic quotient of a symmetric space, and a subgroup and a quotient of its symmetric space, that map between these arithmetic quotients is definable in our algebra. Okay, and so then up to sort of lifting it up into this bundle, which again is not so hard to do, the definability of this map between arithmetic quotients implies the definability of the image, and therefore the definability of our locus of self-dual classes. So this is sort of the outline, right? So we've taken the problem of describing self-dual classes in the VHS, translated into describing self-dual classes in this arithmetic quotient, and then we find that the locus is actually a finite union of smaller arithmetic quotients. And since maps between arithmetic quotients are definable, we get definability, roughly speaking. Right. So I have one more slide here where I want to just say very quickly what goes into this sort of thing here. So again, this is like a not so easy result, so I can't quite do it justice, but I want to at least say what Siegel sets are and sort of give a very brief sketch of what it means to say that this kind of thing is definable. Yes?
Excuse me, I forgot. What does G sub A are? Sorry.
So I fixed one particular orbit of this group gamma, and then G sub A is is the orbit of some particular vector A, and then G sub A is the subgroup of the group that fixes A.
Okay. Okay.
Yeah.
Okay, thank you.
Right. So because so here there's a sort of small technical point, which is that this is stated slightly incorrectly in the paper by Baker, Klinger, Zimmerman. So they sort of claim that any morphism of arithmetic quotients is definable, but it's not actually quite true for any morphism. But there's some condition on the group and the subgroup, but in our particular case, the condition on the group and the subgroup holds. But anyway, so I want to just say in the last slide how these arithmetic quotients actually become definable manifolds. So again, this is much more subtle than it seems at first, because so when you do GR mod K, well, GR is the real points of an algebraic group, right? So this is a real algebraic variety. GR mod K is naturally a real algebraic variety. But then you're quotienting out by this infinite discrete subgroup. And again, infinite discrete things are bad for O-minimal structures. So you cannot just say, well, GR mod K is algebraic, take a quotient, it's definable, right? This doesn't work because the quotient is by something infinite discrete. So instead, you have to take the quotient in a subtle way. What you have to do is you have to take a nice fundamental domain for the gamma action on which gamma acts with just finite orbits. And then you take the quotient of that fundamental domain. And because the group gamma is an arithmetic subgroup, this involves reduction theory for arithmetic groups, as in the big book by Borel and G. So roughly speaking, what you do is you have this notion of Siegel sets, which are certain semi-algebraic sets in the real group that give you almost like a fundamental domain in G mod K. It's not quite a fundamental domain, but it's up to finite error. So when you take the Siegel set and intersect it with translates by gamma, you only get finitely many intersections. And so on the Siegel set, the equivalence relation given by gamma is finite, and then you can take the quotient and get something definable. So this arithmetic quotient, is the model for it is really a Siegel set modded out by the equivalence relation given by gamma. And a Siegel set is the following sort of thing. So again, the general definition is a little complicated, but a specific example that everyone knows is if you take for your group SL2, then the symmetric space is SL2 mod SO2, that's the upper half plane. And it had the usual fundamental domain for the action by SL2Z would be, for example, this shaded region here. And this is much too specific. So for Siegel sets, let me see if I can write on this. For Siegel sets, the sort of set that you would take is some set like this. Some big, easily described set that looks like this, right? it can intersect finitely many of the fundamental domains, but you want it to have a sort of nice straight shape so that it's easily described by some algebraic conditions. This is what a Siegel set looks like in this example. And there's a whole theory of these things in higher dimensions. Okay, and so then when you show that a morphism of arithmetic quotients, like over here, that's definable, what you really have to do is relate the Siegel sets. So you have Siegel sets in the small group GA and in the big group GR, and you have to show that there's some kind of relation between them. Specifically, you have to show that any Siegel set in the small group GA, when you map it into the big group, it lies in a finite union of Siegel sets, or a finite union of translates of Siegel sets. And this is behind this definability, right? In the specific case of these groups that come up in Hodge theory, you can check this by hand by some explicit calculation. There's also a general theorem by Martin Orr that again would give you these kind of definability statements for arithmetic quotients. Okay.
Oh, excuse me.
Yeah, please.
In this final theorem, then is this have the same dimension or what's the?
No. So I mean the group G is bigger than the group GA. So the thing on the left is usually smaller.
Smaller than I think, and also kernel also.
Right. So I mean, before you mod out by gamma A, the symmetric space for GA really embeds into the symmetric space for G because the maximal compact is the intersection. When you mod out by the gammas, it's not necessarily injective anymore, right? But it will be, at least it will have finite fibers.
Finite fiber, okay.
Right, the definability means that the fibers are actually have to be finite. So this is sort of the finiteness comes from this fact that the Siegel set is contained in finite union of Siegel sets. Mm-hmm. Yeah, this part, this arithmetic stuff is super subtle. I mean, one has to be very careful with this. But anyway, yeah. So sorry for being a little bit late, and thanks for your attention.
Thank you very much. So any questions?
So now we have also orthogonal group. Do we have a similar thing for symplectic? I mean, the quotient is definable, that kind of statement.
You have this theorem over here, so that an arithmetic quotient is definable in our alge, and that modulo this condition on Siegel sets, a morphism is definable. That is completely general. The group doesn't have to be the specific group. It can be any reductive group. Okay, so the theorem that Baker, Klingler, Zimmerman prove using this reduction theory is that if G is a reductive group, K is a maximal compact subgroup, gamma is an arithmetic group, then this double quotient is R alge definable.
Okay, any other questions?
So what happens if you run the same argument for anti-self-dual classes instead?
Thank you, good question. Yes, so right. So it may look initially that you have to redo the whole thing in the anti-self-dual case, because of course it should be true in the anti-self-dual case. It turns out you can just do it by a trick. So there's a very cheap trick that I found, which is that if you have anti-self-dual classes, you can actually realize them as self-dual classes in a slightly more complicated Hodge structure. So if I have a Hodge structure of some even weight and I look at anti-self-dual classes, I take an auxiliary Hodge structure, which is the Hodge structure of an elliptic curve of the square with a square lattice, and I tensor by the second symmetric power of that Hodge structure. And then it turns out that the anti-self-dual classes in the original thing correspond to self-dual classes in this tensor product. And so I can just, it just follows from the theorem by just this trick.
I see. So the statement for anti-self-dual classes is the same.
Yeah, is the same thing. Is also true, exactly. The only thing is that the sign changes, right? So in the statement, when I fix some number q greater or equal to 1, and I look at things where the pairing has value equal to q, well, the anti-self-dual ones have a minus sign. In this tensor product, there's a minus sign that shows up, and so then you have to change it to minus q.
Thank you very much.
Mm-hmm.
Okay, any other questions? Okay, so if not the same questions now again, yeah, thank you very much for the talk.
You're most welcome.
Okay, thank you. So let's take a 10 minutes break, and our next talk will start from 10 minutes from now.
Okay,
Thank you.
9 days, okay.